bugs, and we'll address them later. Having said that, Michael, the floor is all yours.
Thanks, Leila. Thanks for the housekeeping bits. Welcome, everyone. Yeah, this is welcome to a VoIP Future rant. So typically the bottom line says welcome to VoIP Future. I recently got into sort of this slightly excited about this topic because it of latency and delay, because it pops up everywhere for actually no reason, at least in my opinion. Before I start to dive into the topic, just some quick words about VoIP Future. So we were founded in 2007, headquartered in Hamburg, Germany, and our mission is to enable premium voice service quality. And so personally, I'm with the company, I think, since more than 15 years. So take that as credentials for what you're about to hear. We provide unique technology for assessing, aggregating, analyzing, and visualizing voice quality information to provide better data-driven insights. And basically, our customers, of which you see a few at the bottom, they use our main product called Crystal for many different services, VoIP services, and in many different networks, mobile networks, fixed networks, enterprise, service provider networks. So basically, I want to say we've seen it all. So having said this, the trigger point for this webinar was the 100th RFQ, which requested some KPI around latency. And I don't know if it was this one or this one or this one or this one. So I dived in to my file system and pulled out some RFQs, and everyone is asking for latency, round trip time measurements, delay, whatever you want to call it. And it's not just RFQs, it's also a topic that pops up in standards, obviously. Here we have the ITU Y1540, which specifies the IP packet transfer delay. We have the G114, which is dedicated to one-way transmission time. We have the GSMA, which also specifies KPIs for round trip delay, one-way delay, mean packet delay variation, whatnot. So delay and latency are everywhere. And the last time that I got this on the table as an RFQ, I thought we need to do this webinar just because you start to wonder why everyone is asking for something that is actually very problematic in terms of measurement and some other topics that we will touch today. So what is latency? Wikipedia says latency is a time delay between the cause and the effect of some physical change in the system being observed. Now that's obviously that's very general, not directly related to voice over IP, but basically you send out a packet on one end and it pops out on another end, and whether that's voice over IP, RTP packet, or something else doesn't really matter. The time difference is basically the thing that is in question. Now, another question that I actually only researched in the course of this webinar is there a difference between latency and delay? And so I wasn't sure before, and actually after this research, I'm also not sure right now because I checked some other sources, but also for the fun of it, I asked ChatGPT, and ChatGPT said latency is a specific type of delay that refers to the time it takes for data to travel through the network. Okay, fine. So basically, a delay, a network-related delay. Maybe more professional and more sort of to the point is ITU G104. This recommendation provides guidance on the effect of end-to-end one-way delay, sometimes termed latency, and an upper bound of one-way network delay. So we'll use it synonymously in this. There's a tendency to use latency for the one-way network delay as opposed to round-trip delays or whatever. But here we'll use it as synonyms, and you will also see why hopefully later on. So what's the problem with delay? The user experience suffers, it's basically common knowledge that the user experience suffers if the one-way delay exceeds 150 milliseconds. And there's this graph on the right-hand side from G107, the E model, where basically it shows that the R factor, which basically can be translated to the MOS. So on the narrow band scale, this R factor is around about the best quality you can achieve with the G711 codec. And you see that as the delay, one-way delay increases, there's a gradual decline, but then there's like this dent around 150, 200 milliseconds, and then it goes down faster. And the reason is that it goes down faster is because from that point on, basically parties in a conversation start to interrupt each other because they think, you know, the other side didn't react and they can continue talking. And so this is the issue. So basically, common industry, common sense is don't have one-way delays beyond 150 milliseconds. So that's fine. So what is the cause of delay latency? Where does it come from in a VoIP context? So here we have a very simple setup. We have a sender of RTP packets or VoIP packets on the left. We have a receiver on the right. And in between, we have two network elements which forward the packets. And basically what happens in the sender, so let's say it's a phone, we have a codec delay. That is the delay basically that the codec algorithm needs to process the samples and create a packet. The other delay that occurs in the sender is the packetization delay, and that basically means the time that you need to get all the samples together that you need for a packet. And depending on the codec, this may be sort of combined with the codec delay. In other cases, like G711, where you basically just where you basically just take samples, individual samples, and convert them, it's separate. But in any case, if you have a 20 millisecond packet rate, the combined codec and packetization delay is something around 20 milliseconds. Serialization delay. Once you have the packet at the sender, you need to put it on the link, and the time it takes to transmit or put the entire packet onto the link, that's called the serialization delay, and that depends on the bandwidth that you have available. Then there's the propagation delay. So once the packet is on the link, how long does it take for an individual bit to travel over each link? It can be approximated basically by the speed of light. It's a bit lower and depends also on the network, but that's around about the magnitude of the propagation delay. Then we have a processing delay. So you have a network element, a router, a switch, whatever. And the processing delay is simply the time that that network element needs to decide sort of to take the packet on an incoming port, decide what to do with it, and basically on which outgoing port to put it. Then if it's in a router, an active network element and working in store and forward mode, then you might also have a queuing delay. If let's say the outgoing link is already occupied, then you will have to store the packet, or the network element will have to store the packet before it actually is able to seize the link and forward the packet again. And then at the receiver side, you have the jitter buffer delay. So basically, each receiver has a buffer to compensate for jitter that may occur on the way, because what you need is a constant packet rate and constant flow of samples. And then when the packet is taken out of the jitter buffer, you have a decoding delay, which is typically very small, but you also need to account for it, basically just decoding the audio and converting it into samples again. So that's the situation. You see there's a number of components contributing to the overall end-to-end latency, end-to-end delay. And so let's say we want to measure it, then the holy grail is the one-way delay. So basically, yeah, what is the time it takes for a packet to travel from source to destination? And if you look at it from a naive point of view, it's super simple. Just note down the time t0 when the last bit left the sender, and note down the time t1 when the last bit arrived at the receiver, at the receiver, and just subtract the times, and there you go. One-way delay equals t1 minus t0. Obviously, that requires super highly synchronized clocks, because we're at least in the millisecond domain, if not, depending on how accurate you want it, actually also much below. And NTP is typically not sufficient. You can do that in your own LAN maybe, but as soon as you cross domains, that is really not the way to go. It is technically possible, but expensive and not generally applicable. So basically, it's typically not an option. What is more practical is what is defined in RFC 3550, where so basically the RTP, the standard that defines RTP, and it defines the round trip delay RTD calculation based on the RTCP protocol, the sister protocol of RTP, and that contains timestamps which basically allow you, in theory, to calculate the round trip delay. And the one-way delay is then approximated by just dividing the round trip delay by 2. And you see how it works here on the right. So you send a packet, it arrives at the receiver notes down the time of the last report it received. So that's its T0. Then basically puts into the response a timestamp called, or actually it's not a timestamp, it's just the time difference, the delay since the last sender report, and then sends it back to the original sender. And then with this information, T0, T1, and this DLSR, you are in theory able to calculate this round trip delay. The problem is that in practice, maybe the forward and the backward path are not the same. They're most of the time, but you can't guarantee, and this would be something that you need to take into account. Also, what if the traffic is different per direction, and there's more congestion on the back path or on the forward path? So also here, there is something that is not sort of always under control, especially if such measurements cross your own network and go off net somewhere. Then we also saw that the DLSR is not reliable, and some receiving devices, or let's say some RTP stacks, are not, how should I say, well, they just put in wrong timestamps, wrong delay measurements. And also, in many cases, RTCP simply blocked in the network, and in some use cases, it's not even allowed by the standards. So, nevertheless, despite all these questions and doubts that you can have about the round trip delay calculation through RTCP, it is the only practical option for voice services, for VoIP services, just because it's uh, just because it doesn't cost anything, or you don't need additional devices or like GPS receivers or whatever at each and every device that you want to measure. So I mentioned some these doubts, what can happen, like unreliable RTP stacks, not providing the right timestamps, etc. And these doubts are not theoretical. And let me show you here one case that we had with one of our customers. They received complaints from their customers. It was back then a residential voice over LTE service, and the customers complained about choppy voice and difficulties with the call setups. And here on the right, the chart, you see that there is 85% of the minutes that we measured here where had a MOS class worse than 3.1, which is abysmal. So it's really, really bad, and the customers had all reasons to complain. Now, the interesting thing is that the tools that they used initially reported a 1 second delay and even more, and also some loss based on RTCP. But basically, they were very, very focused on finding out the reason for this 1 second delay. And once I got involved, my first question was, I mean, if you have a telephone conversation with a 1 second round trip delay, that's what you would complain about. It's not, you wouldn't say, I have choppy voice and difficulties with call setup. I would say, like it feels like talking to the moon. So obviously, I was distrusting the delay from the start, and well, yeah, but they continued in their search, and when we got our equipment in, basically we found right away that the root cause was an underdimensioned link that caused high packet loss and jitters. So they basically had too much traffic for a too small pipe. And once they fixed this, you see here what that did to the master distribution. So basically, all of the traffic is way better than 3.1, and actually 81% were perfect. So, but that didn't just impact this under-provisioned link, didn't just impact the actual user experience of the customers. It also impacted the measurement, and that's actually the reason for this huge delay was jitter, and that impacted the measurement, and that's why they got these huge values. And for our crystal monitoring system, actually, we have, because we saw that not just in situations of jitter or like network issues, but also because we know that some RTP stacks use wrong timestamps or don't provide the right data to calculate a correct delay. We actually have an indicator which says, okay, this delay is above, I think the threshold is 500 milliseconds. It's not trustworthy. We're not going, we're going to flag it. And you typically see that it's always the same devices that cause that. So, okay, so now we saw how difficult it is to measure the delay, but assuming that the delay is actually an issue, something that you in operations want to keep track of, what can you do about it? And here we have a table, and on the left-hand side, you see the different delay components from that graphic that we had a couple of slides back. And so we have the codec delay. That obviously depends on which codec you use. And I would say there's little you can do about it. The type is constant, so the delay is constant more or less per codec, but also the codec is something that you cannot change because it depends on the service. So if you're running a mobile network, you will be using AMR or EVS. If you're using a fixed network, or if you're providing fixed network service, you will be using G711 or G722, or maybe if you're like really advanced, maybe Opus. But in any case, there's not many choices, and even if you disregard this, the magnitude of the codec delay is like microseconds to maybe, a millisecond or something. So sorry. So it's not really something to worry about. Next up is the packetization delay, which depends on the packet rate. Also, this is constant. You typically have like a packet rate of 20 milliseconds. And yeah, the magnitude is therefore tens of milliseconds. And also here, there's not too many options. There's a few codecs that don't even support something less than 20 milliseconds or anything else than 20 milliseconds. You can put several frames into one packet, but in any case, if you put more packets into the packet, then the packetization delay will increase. And if you reduce it, you get more you using your network in an inefficient way, because just the RTP and UDP and IP header, like the whole bloat, will just make the transmission very, very inefficient. So basically, it's 20 milliseconds for packet rate for most services and most use cases, and that's it. Not much you can do really. The serialization delay, like I said, depends on the bandwidth. So if you have like an old modem connection, 64 kilobit per second, then it can take several tens of milliseconds to put the packet on the link. But I mean, that's in today's networks not really relevant anymore. So typically it's in the millisecond range, and also constant. So I mean, you can replace the network to reduce the latency, but yeah, again, due to the magnitude, it's not for most typical connections, it's not really an issue. Processing delay in the network elements, yeah, it's constant, and also in the microsecond range. So really not something that contributes a lot. Maybe even if you have a lot of hops, a lot of times some microseconds gives a number of microseconds, but not a huge delay in the millisecond or second range. Queuing delay. That's what kicks in when you have congestion in the network and the network elements start to buffer. And that is variable. First one here in this list. So, I mean, it can happen or it cannot happen depending on how congested your network is. And if it happens, it's actually the magnitude is quite substantial, also in the tens of milliseconds, just because depending on how long the congestion lasts. So those are typical values from what we see in our customer networks. Then there's the propagation delay. We really don't need to talk about this because speed of light, we're talking about nanoseconds to, I mean, if you're really once around the world, you're in the millisecond range. But again, since you cannot be faster than the speed of light, also there, nothing you can do about it. Decoding delay, again, depends on the codec, again, constant, again, microsecond range. So also forget about this. Digital buffer delay, that's now we're talking. So we have that depends on the packet rate and also on the configuration, whether you have a static digital buffer or adaptive digital buffer in use. But again, that's on the receiver end, and that may not be under your control. So, I mean, it's constant variable. It may or may not be under your control, but it's significant because it's, again, in the tens of millisecond range. So basically, there's not much you can do, and there's basically also only let's say, three significant contributors to the end-to-end delay. That's the packetization, packet rate, but yeah, you can play around with it, but not much, not much to do. And the queuing delay and the digital buffer delay, and both sort of hint on an area where it's actually more fruitful to look uh, for um, for monitoring. So slowly coming to an end, is it even an issue? Is delay an issue? Why would you even want to measure it? I just it's over the internet, and you can say, you know, in a proper tier one voice network, you would take less hops and it would be quicker. I just did a ping from Aachen, where I'm located, to Perth in Australia. It's 14,000 kilometers, you know, as the bird flies, as the crow flies, and light takes about 50 milliseconds to travel this distance. The trace route took 26 hops, roughly 260 millisecond round trip delay. If you add sort of I mean, this is a ping, but if you add sort of the constant VoIP delays on top that I mentioned with typical parameters, 20 millisecond packet rate, 40 millisecond digital buffer, etc. You can add about 120 millisecond, divide by 2, and you get about a one-way delay, mouth to ear, basically, of 210 milliseconds. So yeah, remember from the chart at the beginning, things start to get difficult. Conventional wisdom starting at 150 millisecond. But if if we would go back to the chart now, you would see that 210 millisecond is also not yet catastrophic. And again, what can you do? I mean, you cannot, you know, lay a direct optical connection, you know, between have a fully meshed network and control all devices. So basically, live with it, and it's not too bad in any case. So what's the deal? I mean, I hope I could make some points, and apart from sort of these, you know, theoretical arguments, in 20 years in the VoIP business, I've never seen or heard of any real issues with the actual VoIP delay, not once. And if you have stories to tell, you know, if you have a different view, please you know, ask a question, or you know, get in touch with us, or you know, after I'm done, maybe tell us about it. Every time latency or delay was an issue, we were chasing phantoms, and it all goes down to jitter, which are variations in the delay. So, and that's a problem. In voice over IP, you need a continuous flow of packets. You don't want gaps in the audio, and variations in the delay, which is jitter, are typically then ironed out by digital buffers, and also by buffering in the network. And this is something that you can monitor and also fix if it's, as long as it's your network. But in any case, the aim should be to look at these variations and the root causes, the congestion, and just try to maintain a constant flow of packets. The actual end-to-end delay, or these constant components, that's nothing that you can do about. And so we're coming to the conclusion. Please, like I said, unless there's someone here on the line that says, you know, bullshit, I've had this or that, I would say forget about latency and delay. I mean, ask for it in the RFQs, or write standards about it. That's fine, but for operations, it really doesn't it really doesn't help. It's because it's practically impossible to measure reliably and accurately. The dominant factors are often not in control. and it's an engineering or planning topic, not an operational issues, because a lot of the components are fixed. And really, in practice, it doesn't impact the user experience. Not like even if you make a call once around the world. And I know that all of this is sort of me, old man, yelling at clouds, but also if you're seriously looking for tools that, or if you're asking such questions in RFQs, basically you're doing the same because you're asking something, for something that you really don't have under control or cannot change. What you can change is jitter. So if you have jitter issues in your network, that will lead to audible gaps. And if you try to compensate the jitter, let's say by increasing the dejitter buffer, that will just give you an increased delay. And that's obviously also, I mean, that's what we're talking about. It doesn't help. It will increase the delay, and better to really start at the root. And that's it from my side. Do we have any questions? Or actually, I would really love to hear the story about real end jitter that was causing issues, something that I missed in all my time. Lilach, do we?
No, we don't have any questions
Okay, so I was
for
right.
now.
Awesome.
Yeah, that's definitely a good conclusion.
Okay. Thanks. I like but also you can seriously, if you have a story, get in touch with me directly via LinkedIn or email, whatever. I would love to hear your story, and yeah, thanks for listening, and I hope you have a good day. See you next time.
Bye, everyone. Thank you. Thank you so much, Michael.
You're welcome.